Listen to, we have to hear from Colin. So Colin did his undergraduate assessment at York University and then PhD from Queens, and then went back to this region now. Postdoc in the last 2 years with Professor Johnson. And we'll hear from you. Yeah, so we're looking forward to your talk, please.
Thank you for that introduction. Lower your expectations. All right, so here's the outline for the talk. You'll see it many slides interspaced. I'll start with the introduction. So squeeze states of light have a reduced noise below the vacuum fluctuations in one of their quadratures. And this can be used to enhance sensitivity and interferometry measurements. For example, at LIGO, squeeze vacuum states are being used to help to measure gravitational waves. And they're also fundamental for continuous variable quantum computing. And this is a chip that uses squeeze states to do a quantum computation. So squeeze states in quantum computing, squeeze states are Gaussian, meaning they can be represented by Gaussian functions in phase space. And that's insufficient for universal quantum computing. So with a Gaussian state, you can only simulate a unitary that does a linear transformation. But to do universal quantum computing, you need a unitary. You need to simulate a unitary that can do a nonlinear transformation, and that requires a non-Gaussian state. A particular non-Gaussian state that is used in photonic quantum computing is GKP state, and this can be made starting with squeeze states. So this is a circuit where we have 4 input ports and beam splitters, and then photon number resolving detectors. And into the input ports, we put 4 squeeze states, which then become entangled using the beam splitters. And if we measure the number of photons in 3 of those modes, and we get a certain pattern of on the photon number detectors, then the result is that in the 4th mode, it collapses into this GKP state, which is non-Gaussian. And this is actually being used in photonic quantum computing. However, we have to wait until we get the correct pattern of photon numbers here until we know that we have the GKP state. And the detectors require cryogenic temperatures. So it would be nice to have a more deterministic source of non-Gaussian states, of course, and that would you could generate them at room temperature. Okay, so squeeze states can be generated by a strong pump laser interacting with a nonlinear material. And this interaction can be enhanced in a ring resonator. And to first approximation, you can neglect the entanglement between the generated squeeze state and the laser. But the more efficient that this process becomes, there will be entanglement between the laser and the generated squeeze light, and that'll be encoded in this non-Gaussian state. And so I'd like to share with you some research that we've done on the theoretical treatment of generating these non-Gaussian states using a microring resonator. And then future work is to figure out if this kind of non-Gaussian state is actually any use to quantum computing. So before I get to that theory, though, I'll start with some background on quantum states of light. So I'll start with Fock states, which are a ket here that have a definite number of photons in them, n, and you can write them as repeatedly applying a creation operator to the vacuum state. Now, important to this discussion is a phase space picture of these states. So the vacuum state can be represented by this Gaussian distribution centered at the origin and phase space, where x and p are related to the electric and magnetic field, and they're analogous to a position and momentum operator. And in this case, for this definition of x and p, the uncertainty here in the Gaussian distribution is as a half in either direction. And this represents the vacuum fluctuations. Another important state is a coherent state, which is a displaced vacuum state, and is displaced by an amount absolute value alpha, and there's a phase theta. And this is a model of a classical field because if we allow the coherent state to be time dependent, it'll wind around the origin, and along the x-axis, it looks like a cosine wave. Squeeze states in phase space have their uncertainty squeezed along, say, the x direction here for this particular choice. And to obey the uncertainty product, they're stretched in the orthogonal direction along P. The amount that it's squeezed is given by the squeezing amplitude, and the direction that the noise is squeezed is given by the squeezing phase. So here the squeezing phase is 0. All these states I've shown you have been represented with Gaussian functions, and we can combine them together to form a general Gaussian state. So here I've squeezed the vacuum, and then I've rotated it by this angle, and then displaced it from the origin. Okay, so now I'll talk about the measurement of squeeze states. So we can measure the amount of squeezing by a homodyne measurement. This is where we take a 50-50 beam splitter with 2 input ports and 2 output ports. We have photon detectors, 1 and 2 on the 2 output ports. And in one input, we put our squeeze state, and on the other input, we put a coherent state with a well-defined phase theta and a large amplitude alpha. These will mix together with the beam splitter, and then I'll register an intensity on the first detector and an intensity on the second detector. If I subtract those and measure the fluctuations, that'll be related to measuring the noise in a quadrature X that's rotated by an angle theta by the local oscillator. And then scanning that local oscillator phase, when it's equal to the squeezing phase, I'll see this reduction in the noise. And by the amount that it reduces below the vacuum, I can extract the squeezing amplitude. Okay, so now I'll talk about the generation of squeeze states in a little bit more detail. So we generate squeeze states. Well, one way you can do it is with a nonlinear material that has a second order nonlinearity, like a Chi2 tensor. And we shine on the material a pump with frequency omega p, and this is a strong laser. And through the interaction, say spontaneous parametric down conversion, we generate a signal and idler field at lower frequency, and the energy is conserved. Alternatively, we can use the third order tensor, and this is a process called spontaneous four-wave mixing, where now the signal and idler fields that are generated are higher and lower in energy, but energy is still conserved, of course. And to generate squeeze states with these interactions, we assume the pump is in a coherent state, and we assume that its amplitude is unchanged by the generation process. So the number of photons that go into the signal and idler is much less than the number of photons that started in pump. And if you make this assumption, then the Hamiltonian for these processes will generate a squeezed state. And the amount of squeezing in the resulting state will depend on the Chi2 or Chi3 and the pump energy. So we can enhance that interaction by confining it to a resonant structure like a microring resonator. And here I have a ring that's coupled to a waveguide. And I put my pump into the waveguide, and it will evanescently couple into the ring, where it will its amplitude will be enhanced. And the amount of enhancement will depend on the width of the ring resonances. So the smaller the width, the more field enhancement there will be. And the width is given by gamma bar, which is the decay rate of photons from the ring, which has contributions from an intrinsic decay rate due to scattering loss and an extrinsic decay rate due to coupling to the waveguide. We define this Q intrinsic as a quality factor. The larger Q intrinsic means that there's less loss, less scattering loss. And a loaded quality factor related to the total decay rate, which tells us something about the coupling to the waveguide. We also define an escape efficiency to the actual waveguide here, and it's the gamma extrinsic divided by the total decay rate. And if this can take values between 0 and 1, and if eta is 1, that means that all the photons go out the waveguide and there's no scattering. So a typical photon pair generation rate for, say, this SPDC process in a ring that's made from indium gallium phosphide, InGaP. This is the calculation. We choose InGaP because it has a very large Chi2 relatively. It's 220 picometers per volt. And these are parameters that have been experimentally demonstrated. So for a ring radius of 5 micrometers and a pump wavelength of 775 nanometers and a Q intrinsic of 10 to the 5, for only 10 microwatts of pump power in the input, we can generate 10 to the 8 signal and idler pairs per second. Okay, so now I'll move on to the theory side of things. And this theory is involved in obtaining the solution to the Schrodinger equation for these systems. So to keep track of the lost photons, I showed in the previous slide that they scatter off the chip, but to keep track of them in the theory, we include a phantom waveguide. That's the white waveguide here. And so now the photons have a place to go. So they can couple to this phantom waveguide and we can keep track of them in the theory. And to treat the generation of light in this system, oh, I guess you can't really see the white. Okay, over there is better, yeah. Bad choice. So we're going to treat the generation of light in this asymptotic fields approach that was developed in 2012 for these types of problems. And so we start by expanding the electromagnetic field for the full system in a basis of the asymptotic in and out mode fields that are used in, say, a scattering theory. And we're going to treat the ring that's, well, this dotted box will be the interaction region, which contains the ring. So most of the interaction will just be confined to the ring. And so an asymptotic in field for the actual channel, it looks like a plane wave propagating towards the interaction region in the actual channel with wave number k. And it looks like the other components look like scattered fields moving away from the interaction region in the actual and phantom waveguide. And we can also write down an asymptotic out field for the actual channel. And it's going to look like a plane wave propagating away from the scattering region, and then incoming components in the other waveguides. And finally, an asymptotic out field for the phantom channel. It has a plane wave propagating away from the scattering region in the phantom waveguide, and incoming fields in the other waveguides. So in this basis, we're going to study the SPDC interaction in a microring resonator, just to be specific. And we're going to treat the pump, the blue arrow, as in terms of the asymptotic in field for the actual waveguide. And the generated signal and idler, the yellow and red arrows, will be treated with these asymptotic out fields for the actual and phantom waveguides, because the signal and idler can either scatter out the phantom or they can go out the actual channel. And so here's the Hamiltonian for this interaction written in terms of these asymptotic fields. The B operators will be associated with the asymptotic in fields, and the A operators will be associated with the asymptotic out fields. And those operators commute with each other. So here what happens is that a pump photon written in terms of the asymptotic in fields will be annihilated in the actual waveguide with wave number K3. And then I'll generate a signal and idler photon in the asymptotic out field in the different output waveguides here. So in the actual and in the phantom, and with wave numbers K1 and K2. And lambda is the strength of the interaction. It depends on the Chi2 of the material and the effective area, which is given by an integral over the overlap of the mode profiles in the ring. And these F functions here describe resonant effects due to the ring, and I've drawn the absolute value of them by these black Lorentzian shapes there. We're in the interaction picture, so the time dependence here is given by the dispersion relations for the pump minus those for the signal and idler. And this will be a slowly varying quantity due to energy conservation. And the benefit of this approach is that we don't have to build the Hamiltonian in pieces using, say, couple mode theory. This is what it is. And we're using the full modes of the system. So we maintain the hermeticity of the Hamiltonian. So there's no complex frequencies or anything. And also this asymptotic field approach doesn't just apply to ring resonators. You can use it for other nonlinear generation problems where you have a well-defined interaction region and input. You could then you can identify the input and output fields. Okay, so let's look at a solution to the Schrodinger equation using this Hamiltonian that I just wrote down. And so we'll look for the ket psi of t. And we define the input ket as the psi evaluated at -infinity or on the computer at a very early time. And we write that as a displaced vacuum state in the actual channel, where alpha here is the amplitude of that coherent state. And we're going to look for a solution that factors out the Gaussian evolution with this Gaussian unitary. And that's because we know that, well, we know in general psi of t is going to be non-Gaussian because we have the three operators multiplying each other. But if the entanglement between the pump and the signal and idler is weak, then we know that it's going to be mostly a Gaussian evolution. But we do allow for a residual non-Gaussian ket psi tilde of t, which starts off at vacuum. And if the entanglement is weak, then it will remain vacuum for the total generation process. And a nice thing about this approach, factoring out the Gaussian, is that we can solve the Gaussian problem independently first, and then use those solutions to look at the Gaussian problem later, or non-Gaussian problem later. So looking at the Gaussian problem first, here's the Schrodinger equation that Gaussian unitary has to satisfy. And we get a new Hamiltonian Hg, which is a Gaussian Hamiltonian. And it has two main pieces. The first piece involves the production of signal and idler photon pairs, and that's being driven by the time-dependent coherent state for the pump. The second piece describes the rate at which the pump photons are being depleted by the production of signal and idler. And these W and V matrices are given by or related to the second moments of the Gaussian state. And given the form of this problem, it was shown in this paper that the unique unitary solution is given by a general Gaussian unitary. And I can write it as a displacement operator, a squeezing operator, and a rotation operator, and an arbitrary, a real phase gamma of t. So here's the displacement operator. And this coherent state we're allowing to be time dependent because it can be affected by the nonlinear generation of signal and idler. This is the squeezing operator where J of t is the squeezing matrix. And this describes the entanglement between the signal and idler, and it involves the entanglement over the entire system, so including the phantom and the actual channel. And the rotation operator here, where phi is phi s and phi I are rotation matrices. Oh yes, and I forgot to mention that we can obtain solving this equation, we can obtain solutions for these Gaussian parameters. And once we solve for these Gaussian parameters, then we can use that in the next step to solve the non-Gaussian problem. So the non-Gaussian ket psi tilde satisfies this new Schrodinger equation, where H and G is a non-Gaussian Hamiltonian. And it involves triplets of these operators to do with the pump, signal, and idler. And so here you can see the correlations between the pump, signal, and idler. And these coefficients, again, depend on these V and W matrices, which are just related to the second moments of the Gaussian state. And we've also solved for these solving the Gaussian problem. And the three Hamiltonians are related by this simple relation, where we just do the Gaussian transformation of the original Hamiltonian, and we get the non-Gaussian Hamiltonian after normal ordering, and the Gaussian Hamiltonian here. Once we have this non-Gaussian Schrödinger equation, we can try numerical techniques to solve it. Okay, so the first thing I'll talk about is the Gaussian approximation, which is where we assume there's no correlation between the pump and the signal and idler, and that means the non-Gaussian ket is vacuum for all time. And this results in a Gaussian ket for the full system, which is given by a displacement displaced vacuum state for the pump with a time-dependent amplitude, because there could be depletion of the pump through this efficient process. And that's multiplied by a squeezed vacuum state for the signal and idler. And this is typically what you would expect coming from a ring in this approximation. Of course, this part describes pump depletion, this part describes squeezing, and they're uncorrelated. Now, to take one step into the non-Gaussian ket, we could try a first order Dyson series expansion. So I take my non-Gaussian ket psi tilde, and I'll write it approximately as vacuum plus psi tilde 1, where psi tilde 1 is a small perturbation. So this inner product should be much less than 1. And we find that psi tilde 1 is just simply given by the non-Gaussian Hamiltonian acting on vacuum. So this is the only piece that survives from that large thing. And it just involves the production of these 3 photons. And in this perturbative approximation, the full ket is given by the Gaussian plus the Gaussian with some photons added and subtracted from it. All right, so that finishes that. So now I'll talk about a homodyne measurement in the actual channel in the presence of this phantom waveguide where there's loss. So we're gonna work in the Gaussian approximation for this. I'm gonna ignore the non-Gaussian stuff. So I wait for a long time, and all the light now is in the actual output channel here. And I imagine doing a homodyne measurement to measure the amount of squeezing that I would see in this channel. And my local oscillators now depend on the wave number because they're just going to be some pulse shapes in the waveguide. And I have one for the signal and one for the idler, because I have these 2 kind of fields that are being generated. And this measurement, homodyne measurement, will be proportional to the noise in this quadrature X, where X is given by a sum of the quadratures for the signal and idler. And the operators here know nothing about the phantom channel. These operators only live in the actual waveguide. If I calculate the noise in this quadrature using the Gaussian ket, well, this is what it is. And the M and the N matrices here are just the second moments of the Gaussian state. And if we choose our local oscillators correctly, we should find that the noise in this quadrature is less than 1, and that tells us that there's squeezing. If there was no phantom channel, the way you would choose your local oscillator is by doing a Schmidt decomposition of your squeeze state, and then you would choose the local oscillator to have the same shape as the first Schmidt mode. But in this case, since our squeeze state is kind of smeared over the whole system, and our local oscillator, though, is just defined for only the actual waveguide, choosing your local oscillator to have to be just a part of the Schmidt mode in the actual waveguide doesn't give you the minimum in the noise. So in this case for loss, in this case with loss, we have to use a numerical technique. We use a Lagrange multiplier method to find the optimum shape for the local oscillators to minimize the noise. Okay, so now I'll talk about some results, and I'll show you results for squeezing, and then the non-Gaussianity we get for in-gap rings. So this is going to be my sample calculation. I'll choose a particular indium gallium phosphide material. It has a Chi2 that's quite large, of 220 picometers per volt. I'll select a ring radius of 30 micrometers, and I'll choose the Q intrinsics that have to do with scattering loss for the pump to be 10 to the 5, and for the signal and idler to be 5 times 10 to the 5. And these are experimentally demonstrated values for the intrinsic Qs. Okay, so I'm going to put my pump pulse into the waveguide, and it has a full width half max and time of 0.5 nanoseconds. And its peak power is I'm going to vary that between a microwatt and a milliwatt. And I'll choose the center wavelength for this pulse to be 780.6 nanometers. That just corresponds to the center of one of those ring resonances. And I'm going to assume that the pump is critically coupled to the ring because that gives a large field enhancement. Okay, so now with that system, I'm going to measure the squeezing in the actual channel, and I'll look at this first case called critical coupling, where the signal and idler escape efficiencies are equal to eta, and they're just a half. So everything's critically coupled here, and that gives a loaded quality factor that's quite large, of 2.5 times 10 to the 5. And here we see the blue curve here, so is what I would expect from a homodyne measurement. And so to get this result, we've chosen the optimum local oscillator shapes. And we see here that the squeezing levels off to about 3 dBs. And that's because a lot of the photons are being lost out to phantom, so not many of them make it to this measurement. And you see the red curve corresponds to the squeezing we would have measured if we had access to the entire Schmidt mode. And it's indicating that there's an excessive production of signal and idler photons in the system, but we can only measure so many of them because there's loss. And we find that we can fit this result to this simple formula. To get the minimum in the noise that you would measure, you take the escape efficiency to the actual waveguide, and you multiply by the squeezing you would expect in the first Schmidt mode with amplitude Z1. And if we take the limit, as the squeezing amplitude goes to infinity, we find that this leveling off occurs just at 1 minus eta. If eta is a half, this is a half, and that corresponds to the 3 dBs. Now I'll consider the same material, same system, but with an overcoupling. So now I assume that the signal and idler have equal escape efficiencies eta, but now there's 95% chance for them to go into the actual channel. And the price you pay is that the loaded quality factor reduces by an order of magnitude. So there's less photons that are being generated because the field enhancement is less, but more of them go to the measurement. And here we see we can actually get 11.4 dBs of squeezing, which is nice. And you also can see that in the first Schmidt mode, the squeezing is not as high as it was previously. And that's due to the fact that this quality factor is an order of magnitude less, so there's less photons being generated. And yeah, if we increase this escape efficiency to say 0.975, then we could get, of course, higher squeezing. All right, so finally, I'll talk about pump depletion. So I'm going to focus on a specific case where I put in a milliwatt of pump power into the ring, and the pump will be critically coupled. And I'm working in this Gaussian approximation. And we can calculate the number of photons in the asymptotic infield like this. And it will only depend on the coherent state for the pump. Okay, so here's the coherent state for the pump evaluated at 2 different times. So at the initial time, we choose it to be this Gaussian shape. And at an infinite time, after the process is finished, you see that the Gaussian shape is modified by the nonlinear generation of signal and idler. And so we can calculate the pump depletion by this ratio, 1 minus this ratio, which is the number of photons in the asymptotic infield at infinity divided by what it was at the initial time. And there's 16% depletion of pump photons. So that indicates that there's some correlation between the pump and the squeeze light. This is just plotting that pump depletion as a function of the pump energy. This is the 16% up here. And you'll notice for overcoupling, where we got the best squeezing, the pump depletion is insignificant. And that's because the quality factors are reduced. If I then look at the overlap of just the first order non-Gaussian ket, for critical coupling, where I see a lot of pump depletion, I find that this overlap becomes excessively greater than 1, meaning that there is indicating that there is this large element of non-Gaussianity, and that this perturbative approach is not valid anymore. And yes, so there are strategies. I won't talk about them, but there are strategies to capture the non-Gaussian dynamics in a non-perturbative way. And so I'll finish with future work. Okay, and so in the asymptotic fields approach, there is a nice way to frame this non-Gaussian ket, I believe, and this is for future work. So if you recall, the non-Gaussian ket is a solution of this Schrodinger equation, but I've evaluated it at an infinite time. And the reason why I've done that is because at an infinite time, the pulse has left the ring. There's no more generation of the light. So the derivative of the non-Gaussian ket will go to 0. And if I plug that into the Schrodinger equation, I find that the non-Gaussian ket at this infinite time is an eigenket of the non-Gaussian Hamiltonian, also evaluated at infinity, but with eigenvalue 0. And this is a feature of working in this asymptotic fields approach. And it reframes the problem as looking for the null space of this Hamiltonian, which I think in future work, I think that this might be useful to think of things in this way. But of course, we still have to show that this non-Gaussian ket is actually useful in a quantum computing context, let's say. So in conclusion, I showed you results for InGap, which is a 3-5 semiconductor, and there's other 3-5 semiconductors like L-gas and these are of interest because they can generate high squeezing, and it looks like there's a potential for generating these non-Gaussian states with these materials. And I also showed you that overcoupling the ring produces high measurable squeezing, but there was negligible non-Gaussianity. And alternatively, critically coupling produces low measurable squeezing, but there was significant non-Gaussianity. So this might be a good situation to try to look for this non-Gaussian states. And future work will involve determining the usefulness of these non-Gaussian states for quantum computing. Thank you.
Thank you very much. I think we have to use it for the Zoom. Yeah, beautiful. Other questions? Yes.
Thank you for the great talk. How did you identify the terms that are in the Gaussian Hamiltonian?
Oh, excellent question. I love that question. Let me see. Yeah, so it all starts with this guy. So if you take the guess, if you take our guess here and you plug it into this equation, you find that in order for the non-Gaussian ket to be given by this equation, then you need that the Gaussian unitary has to satisfy this equation with this Hamiltonian. And the Hamiltonians are related by this formula. So this is you can think of this as a definition of the Gaussian and non-Gaussian Hamiltonian. And plugging in our guess into the Schrodinger equation, this is the effective Hamiltonian that comes out. And so you choose a unitary, you choose a general Gaussian unitary, and you do this linear transformation of the Hamiltonian. And then you normal order, and after normal ordering, all the pieces like this are the non-Gaussian. You define that as a non-Gaussian. And whatever's left over is the Gaussian Hamiltonian. Thank you.
Do you want to follow up? Okay.
Hi, thank you for the great talk.
Yeah.
And I'm just curious about, I remember in one of the slides you mentioned that the maximum squeezing that you can achieve in the critical coupling is around 3 dB.
Yes.
So you attribute that to the loss of the phantom waveguide?
Yes, the escape efficiency into the actual waveguide, which does take into account the phantom waveguide, yes.
Okay, so it's due to the coupling. So let's say if we don't have the phantom waveguide,
Mhm.
it's only critical coupling to the waveguide, the bus, and then will you be able to recover the full squeezing or?
No, because you'd have to assume there's no scattering loss.
Yes.
If there was no scattering loss and you just had coupling to the actual waveguide, then you would be able to measure this excessive amount.
I see. Okay, so I just want to confirm that this 3 dB is nothing related to that 0.5 number that you choose for the coupling.
It does, because this 0.5 it takes into account coupling to the phantom waveguide.
So sorry, so okay,
Maybe I misunderstand.
No, so maybe I misunderstand. I saw this is a 0.5 coupling, is coupling coefficient between the ring and the bus.
Yes, but it does. It's the ratio of the extrinsic decay rate by the total decay rate, and the total decay rate involves coupling to the phantom waveguide. So okay, maybe so if there was no scattering loss, this
Yes.
eta would equal 1. Maybe that's the best way.
Oh, okay,
Yeah,
I see.
Okay, that's the best way to explain that. Yeah.
I see.
So this eta equals 0.5 only shows up in the case if we have scattering loss.
I see. May I ask another question?
Yeah, sure.
So I'm wondering, so I see that the depletion is very important of the pump is very important in generating the non-Gaussian state. So I'm wondering if it's possible to throw in some like initial coherent component into your signal and idler. So instead of making it squeeze vacuum, make it squeeze coherent state so that you will deplete more. And
that's also for future work.
oh,
Yeah, within this formalism, we have the ability to do that, to also put in, instead of vacuum for the signal and idler, we could start it off with a coherent state. And that's something that we're interested in looking to work on in the future. Yeah.
okay, thank you. Thank you.
So I'll just ask a follow-up question. So in your formalism, I thought you only included the phantom, but you also have the scattering.
Yes, so
So where do they appear in that solution of the Schrodinger equation?
right, okay, yes, that's a good question. So the operators, well, maybe the best place is to go to where I define these operators. Sorry. Yeah, the operators know about, so here, the indices mu, I've grouped together a waveguide and a wave number. So n here knows about the actual channel, and it also knows about the phantom. So this a mu will have so you can create a signal in, this will have, when I sum over all these indices, you'll have a creation of a signal in, say, the phantom for one of the instances, and then in another instance, you can create a signal in the actual waveguide. So that's how the scattering lives in those operators.
I thank you for it. Thank you, him. Okay, thank you for a nice talk. Can you go to the conclusion slide? I have a question.
I'll just probably faster.
Yeah, sure.
Although I don't know. Well, no, yes, it is. Oops, sorry.
Oh, okay.
Oh, that's good enough.
I'm still trying to understand. So what's the metric you're trying to optimize in this game? I mean, so what you're trying to optimize here?
So I guess one thing I've thought of is taking so I know that, like, say a cubic phase state is important for universal quantum computing. So potentially, what if I could get this non-Gaussian state and show that it's close to a cubic phase state? That's one thing I've been thinking of. But maybe there's other ways to use these non-Gaussian states in a new way that would be useful.
Other questions?
Okay, so thank you for your talk. I have some questions. First is, so if you want to have a non-Gaussian state, then the squeezing is limited by 3 dB.
For that case where we were in
Critical coupling.
critical coupling, yes, thank you.
So because you said if we have critical coupling, then we can have non-Gaussian.
Yes.
And if we have non-Gaussian and critical coupling, then the squeezing is low, right?
The measurable squeezing is low.
Oh, the measurable squeezing is so we can use the squeezing that is there for like quantum computing, but we cannot measure it, right? Or I'm wrong.
That's a good question. If I can go back here. Yeah, so here you see this is indicating that we're generating a ton of photons, signal annihilator photons. But just if we measure them, we get this 3 dB. Now that's a good question though. Does the fact that we have this many photons generated, is that going to lead to can we actually then measure non-Gaussianity? Like, are we, because there's a lot of loss, can we actually measure the non-Gaussianity and show that there's a lot of it?
So my other question is that, so when you say critical coupling, you mean that the coupling is half, the other half all goes to the phantom channel?
That's correct.
So there is no other loss, right?
That-
There is no intrinsic loss for the waveguide or for the ring. Are you assuming that?
Yeah, that hasn't been put in. It's just the scattering loss and then the coupling loss.
So isn't it because like so you are generating a lot of photons, but like most of them are just coupling to the phantom channel, so we cannot use them, right? They're just
Right,
escaping
right.
there. So if we want to use it, then because when we want to, like, for example, use for application, I'm thinking we should like use it in a waveguide or ring or whatever.
Yeah, so that's a good question. It looks, so we are getting a lot of pump depletion in this critically coupled case, but is it going to lead to a usable non-Gaussian state? That will depend on our criteria for non-Gaussianity.
My other question is the material you assumed is indium gallium phosphide, right?
Right.
So does it have like, you're assuming it's lossless, but I mean that in reality is it lossless or the loss is high? The intrinsic loss, I mean, for the ring or for the waveguide. Because when you want to measure it, like the loss that is inside the waveguide or inside the ring.
So here, the scattering loss in the ring, I'm assuming is just coming from surface roughness. Let's say.
But the material loss, I mean that like
I don't think I'd be able to answer that in a way, a satisfactory way.
Okay.
Questions? Yeah, so all the way back and
Thank you for the talk. I was wondering, so what are the perspectives of experimentally implementing this system?
Currently, I'm not sure. We don't have well, that might not be totally true. We are working with Galen Moody from UCSB, who is actually fabricating these ring resonators made from this indium gallium phosphide. So if we can come up with an interesting experiment, then perhaps there could be a platform that's created to run that experiment.
Interesting. Thank you.
Yeah, good. Thank you very much.
Thank you.